Hello everyone, I hope you're all doing well. We are going to have our first online lecture and I bet you are as excited as I am about it. But here we are, and so today we're going to talk about a new type of equilibrium, solubility equilibrium. When you studied reaction in aqueous solution in your first semester chemistry class, you have learned to divide substances into two main categories, those that were soluble and those that were insoluble. And this is kind of a clear-cut classification, but as it often happens when we're teaching science, this is kind of an oversimplification. In nature, things tend to have a more continuous distribution. So really we should talk about substances that are very soluble or lightly soluble, slightly soluble, or mostly insoluble. And in this unit, we will learn how to quantify solubility, and so how to assign numbers to express how much of a substance we can actually dissolve in water. Let's see the example of silver chloride. In your first semester chemistry, you've learned that silver chloride is insoluble. And this seems to imply that if you add, let's say, a tablespoon of silver chloride to a beaker of water, nothing will dissolve at all. And that's not really true. It's just that the amount that will dissolve is actually an extremely small number. So we could write an equilibrium reaction, like the one you see on the slide, and that shows you the stoichiometry of the reaction. So per each mole of silver chloride that dissolves, you're going to have 1 mole of silver ions and 1 mole of chloride ions. So this means that because of the 1-to-1 ratio between the two, the amount of each of the two ions is going to be exactly the same. Now let's see what happens at the very beginning when we just added silver chloride and it has not dissolved yet. We have two separate phases. On the top we have the liquid phase, that is still water with nothing yet dissolved in it. So the concentration of chloride ions and silver ions in the liquid phase is 0. At the bottom we have the solid phase, that's made of silver chloride solid. Now we cannot really talk about the concentration of silver chloride in the solution because it's not in solution, it's in a separate phase, it's in the solid phase. So its concentration in the solid phase, where there is nothing but silver chloride, is going to be 100%. Eventually, some of the ions will start dissolving, so you will see that the concentration of chloride and silver ions will progressively increase in the solution. Of course, you're going to have less solid at the bottom, but its concentration in itself is still going to be 100%, as long as there is at least a tiny bit of solid left. But as the concentration of the ions in the solution increases, also the chances that they could collide into each other are going to increase. And that would lead to reprecipitation of the ions, so we call that process crystallization. So the rate of crystallization increases over time because the concentration of the ions in the solution is increasing. Eventually, that rate is going to be equal to the rate of dissolution. And when the two rates are the same, the concentration of the ions in the solution is going to stay constant over time, and we have reached an equilibrium. You need to remember that in equilibrium, it's a dynamic process. So you're still going to have some ions dissolving, you're still going to have other ions precipitating. It's just that the amount of the two is the same. Therefore, the concentration will stay constant over time. This equation is showing us the dissolution reaction of magnesium hydroxide. In this equilibrium, this time the stoichiometry is slightly different, because for each mole of magnesium ions that you produce, you get 2 moles of hydroxide ions. So being an equilibrium, we can write an equilibrium constant. We need to remember though that this is an heterogeneous equilibrium, and so based on what we learned in the unit about equilibrium, substances that are labeled as solid or liquid will not appear in the equilibrium constant. So the equilibrium constant for this dissolution equilibrium is going to show just the concentration of the two ions. The other important thing that you want to notice is this exponent here. We have an exponent of 2 because there is a coefficient of 2 in front of the hydroxide. So how do we measure the solubility? When we use generically the word solubility, what we mean is the amount of solute that dissolves in 100 milliliters of solution. Now, typically, these solutions are pretty diluted, and that means that the density of this solution is pretty much the same as distilled water. That would be 1 gram per 1 milliliter. So we can either express the solubility as grams of substance per 100 milliliter of solution, or we can express it as grams of substance per 100 grams of solution. If the solution is very diluted, it's not going to produce any difference in the numbers. Molar solubility, expressed as molarity, is the number of moles that you have dissolved in 1 liter of solution. So it has, in all respect, a molarity, and it has therefore the same units. It's typically indicated with the letter S. Finally, we can use the solubility product to communicate the amount of substance that we managed to dissolve. So in general, we can expect that if something is quite soluble, we will find a large number for solubility, a large number for molar solubility, and a large number for solubility product. So at this point, I would like you to watch a movie on YouTube. So you have to follow this link, copy and paste it in a browser, and I would like you to stop watching the movie at about 3:35 and set the movie aside, come back to this PowerPoint, and then we will see the rest of the movie later after working on some exercises. You will see that there is a compound that is mentioned at some point, that's hydroxyapatite, and they use that because it has relatively complicated stoichiometry, so it kind of offers a better way to show you how to write Ksp. But it's actually an important compound. It's the most abundant constituent of your teeth and bones, and it's particularly abundant in the enamel of your teeth. So it's a really significant compound in your body. So see you after the movie. Okay, so let's have a look of some exercises. Let's start simple and add difficulties one at a time. So in this problem, they want us to determine the Ksp of silver bromide, and we are given the molar solubility. So molar solubility is 5.71 times 10 to the minus 7 moles per liter. So the first thing you want to do is write the reaction that represents the equilibrium of the solution, because that shows you the stoichiometric ratio of all species that are relevant. So this tells you that there is a 1-to-1 ratio between silver and bromide ions. And so if the molar solubility is that number, that's how many moles of silver bromide I can dissolve, that's also how many moles of silver ions I will have in solution, and is also the same number for bromide ion. So the next thing, you want to write the Ksp for this reaction. Again, remember that is an heterogeneous equilibrium, so you will not use the concentration of the silver bromide. And the other important thing is that you have a coefficient of 1 in front of each of the two species, and this means that there are no exponent in the expression of the Ksp. So all you have to do really is plug and chug, right? You get a really small numbers. Now make sure the setting on your calculator are such that you can handle these small numbers without complications. Some calculators may decide that the number is so small that the calculator may round it down to 0. In this example, we need to determine the Ksp of calcium fluoride. So the formula of calcium fluoride is KaF2. So the first thing you want to do is write the equilibrium for the dissolution of calcium fluoride. And so this will make, and balance it obviously, so you will immediately notice that there is a coefficient of 2 in front of the fluoride. So the first consequence of this is that the concentration of the fluoride is always going to be twice as big as the concentration of the calcium. When we write the Ksp, we need to remember to add an exponent of 2 to the concentration of the fluoride. So at this point, we can actually plug the numbers, and you can see that there is, we had multiplied by 2 the concentration for the fluoride, and we also have added the exponent. So just remember those 2 steps. So in this example, you have to calculate the Ksp of mercury bromide. Now you may remember from general chemistry 1 that you have 2 mercury ions, mercury 1 and mercury 2. You could be tempted, if you don't remember some details from Gen Chem 1, to write the dissolution reaction as such. The problem with this is the formula of mercury bromide is incorrect. Although it's true that mercury and bromide combine in a 1-to-1 ratio, the formula is actually this. The reason for that is that there is a body of experimental evidence that shows that mercury 1 is actually bonded to another ion of mercury 1 in a dimer, and there is a covalent bond, so that makes the formula H2Br2. Because of that, the dissociation looks a bit different, and so when you write your Ksp, you actually need to multiply by 2 the concentration of the bromide, but not the concentration of the mercury, and the concentration of the bromide needs to be elevated to the 2nd power. If you would have written the other formula, you would have just squared, basically, 2.52 times 10 to the minus 8, and this would have given you a different number as a final result. Okay, so depending on the mood, I guess, of who's writing the exam, if they want to be a little bit tricky, they may put this example in a test. So here we have barium phosphate. The difficulty here is due to the formula of barium sulfate, right? So we have like the worst case scenario in terms of coefficient. There's a coefficient in front of each of the 2 ions. So when we write the Ksp, the concentration of the barium is elevated to the 3rd power, the concentration of the phosphate is elevated to the 2nd power. You also need to remember that the 2 concentrations are going to be different, and they are in a 3-to-2 ratio. So when you're plugging the numbers, that's how it should look like. You can also see how extremely small is the result of this multiplication. So really we are talking about extremely small numbers. So far we have never used the molar mass in any of the problems. That's because the solubility was also always given as molar solubility. If the problem would be giving you grams, you would have to first convert grams into moles. So that would be the calculation slightly longer. Let's have a look at this problem. You have a saturated solution of magnesium hydroxide, and you're given the pH, and so that can be a little confusing at the beginning. You need to calculate the Ksp. So we start as usual writing the reaction for the dissociation of magnesium and hydroxide. The Ksp would look like that, so nothing particularly new now. The problem is that it looks like really they are not giving you the concentration, so you don't have the numbers to work, but you are given the pH. Now you might remember from your the unit about acid-base equilibrium that the pH is minus the logarithm of the concentration of the H plus, and the pOH is minus the logarithm of the concentration of the OH minus. So, and the two, when added together, gives you 14. So if you're given the pH and it's 1017, we can calculate the pOH by a subtraction. 14 minus 10.17 is 3.83. So that's the pOH. So we can use the antilog to calculate the actual molarity of the OH minus. And so that would correspond to the concentration of the OH minus would correspond to this number. So the concentration of magnesium ions is going to be half of that, because they are in a ratio of 1 to 2. So now you have both numbers to enter into the equation for the Ksp, and you can calculate the Ksp. Let's see now a different kind of problem. In this problem, we are given the Ksp, and we need to calculate the solubility. Okay. So let's write the Ksp expression. So we have a simple molar ratio of 1 to 1. It could be useful in these problems to use an AC table to solve it. So let's see what we have in the AC table. The initial concentration for both ions is 0, because the initial moment corresponds to us not having yet added the solid to the solution. So to speak, the solid is still on the spoon, and there is nothing yet in the beaker. Therefore, the concentration is 0. Also, you may notice that there is nothing for AgBr solid, because it's in a different phase. So it's excluded from the calculation. For the same reason, it's excluded from the expression of the Ksp. The change is positive because the concentration from 0 can only go up. So by the time we reach equilibrium, both concentration of silver ions and chloride ions is going to be X. As a consequence, the Ksp corresponds to the square of the solubility. The solubility can be calculated as the root square of the Ksp value. In this example, we want to calculate the molar solubility of tin hydroxide, tin 2 hydroxide. So the formula is SnOH2. The Ksp therefore will have this form, so we need to remember our exponent here. We can approach the problem with an IC table. Again, we have nothing for the solid because it's in a different phase, so its concentration in itself is constant. The initial concentration is 0 for both, but the change for the hydroxide is twice as big as the change for the tin because of the coefficient of 2. So at equilibrium, the two concentrations are going to be X and 2X. You can then plug these numbers into the Ksp expression. We know the value for the Ksp. So the Ksp is equal to X times 2X to the second power. Now the most common mistake you will do while solving this problem is assume that this part of the expression is going to be equal to that, and that's incorrect. So just watch that. Then you will have to calculate the cubic root, so that you may want to familiarize yourself with your calculator and see how you can do that. At this point, we are done with the PowerPoint, and I would like you to go and see the rest of the movie. So you should have stopped at 3:35. You can start from there. See you tomorrow probably for the next PowerPoint presentation. Stay safe.